Thank you to the organizers, and especially to Peter for inviting me to talk about aging today. I'm going to describe the efforts from my lab and in the field to try to target healthy longevity and to see if we can extend human health span. This is the data for Singapore. However, it's quite similar for almost every country. It's just progressing at different rates. Singapore is aging rapidly, and so in 10 years, we'll have 1 in 4 people over the age of 65. And what that means is there will only be 2 people working for every retired person, as opposed to over 8 in 2000. So what we have here is a lot of older people who are in declining health, and so we have an issue with quality of life in a large percentage of the population. But we also have an economic issue because there are not enough workers to take care of all the retired people. And this really matters if people are sick. So if we look on the right, here are people in Singapore, the cost of their health care for annually, if they're over 65 with no chronic illnesses, that's about $2,100 US, but it goes up almost 6 times if you have 2 or more chronic diseases. So this emphasizes the importance of keeping people healthy late in life. But currently, both research and medical care is really focused on sick care. So we treat diseases as if they're all different, try to develop separate cures for them, and try to treat people for each one. The main point of aging research over the last couple decades have been to demonstrate the notion that aging is the biggest risk factor for all of these chronic conditions. And this suggests that if we not only tried to cure disease, but tried to target aging as a means to prevent disease, we would have a much bigger impact on health span. But even this is limited, as I learned last year, because if you look down at this table on the left, what you realize is that aging is by far the biggest risk factor for mortality due to COVID-19. All of these other blue boxes are like cardiovascular disease and diabetes, pale in comparison to being over 70 years of age in the orange box. And by the way, that's not just true of COVID-19, it's true of influenza and many other infectious diseases as well. So really we should be showing the panel on the right, which is that aging is not only the big risk factor driving chronic diseases, it's the big risk factor driving the severity of infectious diseases, and it's also mediating functional decline. So I believe that this is really the biggest medical challenge of the 21st century, and if we can slow or reverse aspects of the aging process, we can have amazing effects on all 3 of these issues that occur with aging. But none of that matters if we can't do anything about the aging process. And as you'll see here, there are many different types of interventions that have been linked to slowing aging. There are 3 circles to focus on. This bright red circle is lifestyle interventions, and that's largely things like changing your diet, exercise, sleep, maintaining stress. We already know that some of these things work for aging. Exercise extends median lifespan and improves health span by many, many different studies. The challenge here is really getting people to comply with sustainable lifestyle change. And the second circle is really what we're really in at the moment in the field: drugs, small molecules, natural products. And I'm going to tell you about one of those today. Many of these extend health span in animal models and lifespan, and we're just starting to test them in the human population. And then there's a third circle here, which I'm not going to go into today, which is more futuristic approaches. For instance, stem cell therapies, gene therapy, organ replacement, and they may have even bigger impacts in the long term, but we're really not at a point where we can easily test most of those in humans yet. So the key thing right now, in my mind, is to test the small molecule interventions and validate that they can slow or reverse human aging. And our lab works on a number of these small molecules, both in animals and increasingly in human studies. And I'm just going to tell you about alpha-ketoglutarate today for the sake of time. This is a safe, natural product that can be taken in relatively high doses with no reported toxicities. And it was discovered through a collaboration between my lab at the Buck Institute and also in Singapore with Ponce de Leon Health. and they were looking for natural products that impacted lifespan using C. elegans and also mouse models. And so we initially screened a bunch of compounds in C. elegans and then tested them in mice starting at 18 months of age to see if we could delay the aging process and extend lifespan, but also increase health span and reduce frailty. And I'll just show you a little bit of that data. So we're starting at 18 months of age in males and females. This is the survival curve. And if you look at this, it's relatively modest. There's a 5 to 10% extension in females that's significant, and a smaller effect that's not quite significant in males. We've repeated this 3 times now with similar results. So small but interesting effect on lifespan. But what got us excited was the effect on health span. And we assessed that in part by looking at frailty using a index that was developed by Susan Howlett and colleagues, several years ago. So you calculate for each dot here is an animal, and the higher the score is the higher the frailty. And so as the animals get older, you see that the frailty goes up. Blue is controls, magenta is AKG treated animals. It goes up faster in the controls, but this is a difficult way of looking at the data, because if you take this animal here, which had very high frailty at 23 months, it was dead by 25 months. So a lot of the animals are dropping out as we go along, making the curve difficult to assess. So we went back after all the animals died and rescored the animals as a percent of their lifespan when we took the frailty measure. So in other words, all of these data points were in the 50 to 60 percentile of the animal's lifespan, 60 to 70, 70 to 80, 80 to 90, and 90 to 100. And that gives you a much better way of looking at the data. And you can see that it consistently goes up in the control animals, and that's largely mitigated in alpha-ketoglutarate treated animals. This is females, the male data is the same, and you have about a 50% reduction in frailty. So by virtue of the fact that we're modestly extending lifespan, but significantly, much more significantly reducing frailty, we think we're compressing morbidity in these animals. And we've shown that they have a lot of different features. For instance, AKG improves adult stem cell function, it improves metabolic flexibility, enhances respiration, it alters the microbiome in interesting ways that we're just beginning to understand. We see a dramatic reduction in inflammation, and we're starting to get data that aging biomarkers in humans are also affected by AKG. I don't have time to tell you about this today. I do want to focus on though, and that's exercise, because bodybuilders and athletes have taken alpha-ketoglutarate for many, many years because they think it enhances performance. And so this is just 3 different reports online that I just pulled off in a couple minutes. There are many others if you want to look at them. AKG enhances athletic performance, it enhances wound healing, which is important after damage to muscle and rigorous exercise, and it enhances muscle building. And so we wondered why that might be. And what we're able to show is that unlike many cell types which don't take up much alpha-ketoglutarate, red blood cells readily take it up, and it's the rate-limiting reagent in red blood cells for glutathione production, which is an antioxidant. Red blood cells really care about this because they're carrying around lots of oxygen molecules with hemoglobin, and they're susceptible to oxidative damage. When you take red blood cells and add AKG, in 2 hours you can double the glutathione levels. And in the mice, a week of administration can almost double the AKG levels in the animals as well. So one thing we think is happening is very simple. With glutathione going down with age in red blood cells, if we add AKG, we drive glutathione production back up. This restores resistance of red blood cells to oxidative damage, improves their oxygen carrying capacity, and that's good for peripheral tissues, including muscle. So it's good for exercise. It's also good for aging in a case where people suffer from frailty and sarcopenia. So we think this is one property of AKG linked aging, and it also might be interesting because the reduced oxygen levels in the blood are a primary risk factor for survival in severe COVID-19 patients. So this is acute respiratory distress, and if AKG can improve oxygen carrying capacity, it may help get people through brief conditions of acute respiratory distress and keep them alive until the inflammatory cytokine storm can be mitigated. In any case, a number of aging molecules have now been linked to COVID-19, either through protecting people from getting the disease or getting the severe forms of the disease. And so I think there may be some effect there that's worth following up. And it may be that these longevity molecules dampen or alter the immune system in ways that make the body more able to fight off viruses. Clearly, more study needs to be done there. The real challenge for us, though, is to get beyond mice and get into humans. And so there are two clinical studies being performed right now, one by the company at University of Indiana and one that we're planning at National University of Singapore. They're similar in nature, 45 to 65-year-old participants, reasonably healthy, placebo-controlled. And what we're really looking at here is aging biomarkers and inflammatory markers as outcomes. And so we think these new aging biomarkers that have become available are great tools to determine whether interventions are actually working in humans or not. And so the first one we're doing with a small molecule is AKG at NUS, but we're going to test 5 to 10 other small molecules and compare and contrast which ones work best in the human participants. And so these interventions have been a major discovery in the aging field, but the biomarkers are equally important. The first generation of really AI-based biomarkers came out from Steve Horvath and from the Hannon lab, where they took single omics data sets and used the AI and chronologic age to optimize to predict chronologic age. And essentially, the divergence of the prediction from the chronologic age is supposedly the biologic age. In other words, if I'm chronologically 54 and this AI says that I'm 47, it means I'm aging well. These markers have proven to meet many of the criteria that you would want for a biomarker of biologic aging. So they're not fully validated, but we think they're very, very promising. There's now a second generation that are optimized based on not just chronologic age, but clinical biomarkers as well. And hopefully a third generation that will come out soon that really personalizes it so we can look not just at an individual's biologic age, but at their specific organs and systems. And maybe be able to determine not just when they're going to get chronic diseases, but what chronic diseases they're most likely to get. So in Singapore, we're really interested in assessing these biomarkers. And so the first thing we're doing is a cross-sectional study of Singaporeans looking at a wide range of different potential markers of aging. DNA methylation age is probably the most well-known, but we're also looking at age based on 3D facial reconstruction from collaboration with Jackie Hahn's lab. We're looking at metabolomic aging, inflammatory markers, and then some more standard measures like arterial stiffness, body composition, cardiorespiratory fitness, etc. Hopefully we can integrate this together to get a thorough understanding of biologic aging and then use those markers for interventions. And if you look at the interventions we're doing, this is the cross-sectional study here on the left, that we're also looking though at the effects of exercise. In addition, the alpha-ketoglutarate study. And again, we're going to add 5 or more small molecules in addition to alpha-ketoglutarate so that we can really figure out which ones are working best. There's a lot of personalization studies and a lot of collaborative studies as well with departments in the hospital that are interested in specific aspects of aging and metabolism. Just to give you an example, we're working with surgeons doing bariatric surgery to see if an obese individual's bariatric surgery is sufficient to reduce their biologic age as well as improve their metabolism. So there are a lot of studies like that. We also have some collaborators outside of NUS, and we're always looking for people interested in collaborating. So if you have a small molecule you'd like to test, or a biomarker or diagnostic, we're happy to discuss that and see if we can work together. And with that, I think I need to stop because I'm probably out of time. Thank you very much for taking the time to listen to this, and I hope next time I can visit the beautiful city of Prague and meet you in person. Thanks again.